Okay, so today's lecture is going to be the last lecture where we cover new material. Now, with this particular section, lecture 01, my expectation is on Monday that I will cover, Tuesday, a summary of all of the material in the course, and I will try and go through a final exam. The other section has 2 more lectures, so I will do the same thing plus another exam. I probably will not be annotating those notes, so I'll post all of the notes for next week, Tuesday around, hopefully at 5, but it depends on how energetic I am at that time, but Wednesday morning for sure. I have office hours today. I am somewhat hesitant to have office hours next Friday, as you all have the MIE 301 exam the next day. Is that right? So I don't think that's going to be very helpful for you. So I do plan to schedule some office hours the day before the exam, and we'll figure it out later. But we were talking yesterday, about the change in drag as you roughen a surface. So here we have, again, that same chart, and I'll talk about it in more detail when I do the example. But there's a drag crisis, a sharp drop in C sub D at Reynolds number of about 4 times 10 to the 5th. For golf balls, this trips much earlier, and you can see that on the curve. And again, this is not from the text. I actually was looking for this because I was asked a question, and when I was asked the question, I said, of course, White has a copy of this exact same curve. It doesn't. So this one is from another text, but it's really useful to sort of see why exactly surface roughening and golf balls do what they do. Transition shifts to the left from 4 times 10 to 4 times 10 to the 4th, which is significant, and again, same sort of point. If you're a really good golfer, you can do a lot of things with that. Diameter of a ball is roughly 1.7 inches, 0.0429 meters. Velocity to 61 meters per second, density and viscosity. And we can calculate from that what the Reynolds number is. And I've, of course, given you the answer just below. But the Reynolds number is equal to U d renew 61.0429 over 1.46 times 10 to the minus 5. So 1.79 times 10 to the 5th, which is below that smooth value for a sphere, but it's above the value for a golf ball. So if we do that for a smooth ball, we can calculate from the previous figure C sub D equals 0.51, and C sub D is approximately 0.25. And that's coming off of this curve, and I have helpfully already drawn in sort of those points for this particular example. And so if you look at this example, you can see that the golf ball has sort of hit a region with low drag versus the smooth ball over here. So this is one of the reasons why you do these changes. Now, one of the problems, of course, is that I do not have an equivalent to the Holland equation, and I'm going to redo these types of, or I'll show you this figure again. This is an interesting experiment. I think it was done by one of the US Navy labs years and years ago. In fact, it was in my undergrad fluids text, which was white. And at that time, that's a great photo. So all they've done is they put a tiny bit of sandpaper on the nose of the sphere. It's the same speed in both of these cases. And they have changed where the wake location is. So that's that 82 to 120 degrees that we talked about 2 lectures ago. And you can see from that, if you did sort of a control volume, that would change what your pressure drag is, the body force. So that constant term is going to be 1/2 1.225 61 squared 0.0145. And that's right here. So I can put all of that together and I get 3.3 newtons. If I put in the C sub d, I get 1.68 newtons. And for a golf ball, 0.83 newtons. So that's why you're getting the much longer sort of drive length with a golf ball. That's why we've gone through all of this effort in order to design these things to make them work better under different circumstances. Hold on. So this is actually a really good image to work with. So if you were doing a control volume on that, everything that's in the disturbed zone is low velocity. And so you know that with low velocity you have high pressure. And that high pressure is acting on the control volume. On the front side of that sphere, on that ball, you have low or the same velocity, so the same pressure in all of these cases. And so if you look at that from that perspective, I don't have the right colors for this, but there you go. You have a pressure difference now that is determined by the wake width. And the wake width is the easiest thing to work with here. And so you have a very large low pressure region that you don't have in the turbulent case. And that's why there's a difference. You have added friction because in the figure on the left you have no sandpaper on the nose, nothing's happening. On the figure on the right, you have sandpaper, and so you've added frictional forces, so a C sub F into it. So you pay for things, but you don't pay as much as the benefit that you get. Any other questions on this? Drag forces on immersed bodies are defined using characteristic area. So that's, we use sort of an area, and it's not always going to be clear what that area is. Again, a lot of this is going to depend on experience. You also have to look at the data that you have. So you are going to be dependent on charts, on tables, and so however you define them, you have to know that you're defining it the same way as the chart is that you're using for your data collection. There's region, okay, boundary layer, velocity profile, shear stress. All of that, in this particular case, shows a slow laminar flow. And the reason I know that is because there's no separation off of that sphere. The flow goes all the way nicely around and goes on the other side. And in these cases here, I know that that's roughly below Reynolds number of 10. And I don't remember, yeah, here we go. And I know that because there's a lot of tabulation of data. So it's actually Reynolds number of 5. As you increase your Reynolds number from 5 to 40, you start to have a small recirculation zone. The flow stays attached, but in the rear of the sphere, you have a small zone where you have flow that is being separated and is sort of doesn't move, doesn't change much, but it stays in place. From 40 to 150, you have a separation that occurs. And again, if you have a chance, there's a lot of work out there, and YouTube is really good for flow visualization downstream of cylinders and spheres. And there's also a lot of numerical work now. And so a lot of high performance computing that's been done to look at this. But you start to see a uniform sort of shedding that occurs. Again, these sort of rotating sections of fluid are sort of uniform in shape, and they sort of persist. Then you go to about, you have a transition zone, and these vortices still appear. So again, lots of work done on this, looking at something called coherent structure identification. The important point is those vortices are really important if you want to model these flows. And so that goes and persists to 3 times 10 to the 5th, so 300,000. And you have a vortex street that is fully, the vortex street is everything downstream of the sphere. And then you have transition, and then more importantly, you know, it occurs over this wide region. We typically can sort of pull it out. We see something that looks the same in the turbulent flow as it did in sort of here and here. But that sameness is not as helpful as you'd hope it would be. This cartoon is great. It shows a lot of things. We spend a lot of time trying to identify these. And so those are the muscles that drive the flow. And if we want to model that, we have to model what's happening. So I did threaten you with the same figure again. So these are two. So this is the laminar versus turbulent boundary layer here. And all this is, again, is that this the nose of the sphere, they put a small piece of sandpaper. Nothing major. And so it's dropping at the same speed. So the speed on the left and the speed on the right are the same. The only thing that has changed is the roughness of the nose. And it's not a huge patch, it's just there. They have higher skin friction, but one of the things that these turbulent boundary layers do is they stay attached much longer. And we use that a lot when we design aircraft or anything of that nature, because it's a great way to deal with things, even though you pay for it with friction. So total drag is reduced, even though you increase the friction drag. And often, when you look at sort of current design, most of the design is focused on reducing friction drag because they've done already a really good job on pressure drag. So that's kind of a zoom in on the golf ball. And you kind of see, again, a big difference in terms of the behavior with the golf ball on the right-hand side there. You see it for a smooth sphere and then for a roughened sphere, so the golf ball. And you'll notice, again, the only difference between the two is where the detachment occurs with respect to the boundary layer. So you maintain it from 82 degrees, and you maintain it for another 40, basically, through 38 to 120. Total drag is actually going to be a combination of both body forces, pressure drag, and friction drag. And so we deal with both of those by trying to streamline things. So you can see, for example, in the upper figure, that as there's a separated flow, you still have a separation that occurs. You can't get around it from geometry. You can try and deal with it by essentially extending that body by a little bit. So we do a lot of effort. So all of the stuff I talked about in terms of the 1920s work done by NACA was devoted to the idea of trying to sort of quantify how these things behave. And the relative drag force becomes much lower, but the skin friction component, you can see in terms of the little boxes, one on top of each other, the shaded area is the skin friction drag, the unshaded area is the pressure drag. And the pressure drag is very high in the laminar case, but the skin friction is relatively low. But when you go to turbulent flow when you go to skin friction drag you don't really change too much in this case. They're the same Reynolds number, but the pressure drag goes way down. So blunt bodies are dominated by pressure drag, due to having a large flow separation. Streamlined bodies are dominated by skin friction drag as flow separation is minimized. Is a chair dying out there? Okay. You also have done a lot of work looking at Bernoulli's equation. So all of the stuff that you've done all the way back, you can move your chair if you want to. You don't have to sit there. We've done a lot of work, so you're going all the way back to chapter 3. You have the Bernoulli equation, and we're not dealing very much with height. We deal mainly with pressure and velocity, so kinetic terms. For airfoils, you essentially accelerate the flow because you're making the total cross-sectional area smaller. On the bottom surface, you have a lower velocity but higher pressure, and that's where the difference between pressures then become the lift that you experience on the airfoil. And these sort of simplified pictures are really what we have tended to look at in all of these cases. So you're not doing anything different other than trying to figure out ways to improve aerodynamic characteristics. So again, streamlining. Here you have a large rectangular object at A, a slightly curved object at B, and you have at C a streamlined body, and finally a body with similar sort of drag as the streamlined shape. And the only difference as you go through is you have these right angles here. You've curved the front, and by curving the front, you've dropped the C sub D from 2 to 1.1. Then if you streamline the rear, getting rid of the wake, essentially covering it and allowing the flow to recover all the way through, you end up with CD, which is equal to 0.15. That's the equivalent to a very small sphere where you've allowed, or you've done no streamlining other than just the front area. Any questions so far? So a lot of the chapter, or this part of the chapter, you start to look at a whole bunch of different charts that describe square cylinders, half cylinders, plates, and you can see that C sub B based on frontal area goes from 2.1 for a square cylinder, 1.2. So the front curvature does help. Just 1 second. The plate, which is going to be a squared off end, is going to have a similar sort of drag coefficient as a square cylinder. Turning that square cylinder by 90 or 45 degrees, 1.6. Flipping the half cylinder increases the drag, and thin plate normal to a wall decreases the drag too, because you have a lower drag coefficient near the wall because you have zero flow near the wall. Half tube equilateral triangle, sure, that's going to be pretty good. The equilateral triangle flipped around goes from 1.6 to 2 because you have a large planform area that you're looking at the very front. And half tube, for example, you're catching the fluid and then it's trying to go around. So there's a lot of things that you start to look at. These are 2D bodies, not 3D. You had a question?
To make a standardized comparison, are all the characteristic areas kept the same for all these geometries?
All of the characteristic areas are going to be based on the frontal area. So, for example, the square cylinder is going to have one of the sides essentially multiplied by another side. In this case, the frontal area is going to be that. So you have to measure out what the frontal area is going to be dependent on what's happening. Here, for example, you have a frontal area that's going to be based on this distance right here. It's the same one for this case because they're both oriented 180 with respect to each other, but the flow reacts differently. And so you need the chart to sort of calculate that. And so this is where you're going to spend a lot of time looking at charts, identifying what the thing looks like, and then correlating that to what you see. Same sort of thing. So earlier I showed you the top plot. This is starting to be a bit much. I have a curved surface that is approaching. And so if you look at the top, you have L over H, which defines everything. You see that as L over H increases, so longer and longer, you go from a C sub D at 0.5 of 1.16 to 0.64. All of those also with the same sort of thing happens when you look at L over H for a, what do they call it, a flat nose section. So again, shifting things and making things happen in various orientations is what defines it. Then you have the elliptical cylinders, 1 to 1, 2 to 1, 4 to 1, 8 to 1. Again, you're going to spend a lot of time looking at those figures. Yeah. Is it my microphone? Guys, I'm going to switch to the podium and try that. God, this is... Okay, so for 3D bodies, same sort of thing. C sub D based on frontal area, various shapes. You'll notice that, though, the value changes. So cubes, cylinders, is there a cylinder in this? Yeah, cylinder in the, on the right, L over D, and you have an L over D that goes from very comparable 1 all the way to infinite. And you can see that it goes to 1.2. It sort of gets to a minima at around L over D of, I'm going to say, 2. Or no, 1. L over D of 1. Sorry. You have C sub D of the average person. And I don't know what the average person's size is. There are different average people depending on what you're doing. And what will happen is you have to define them for different cases. So average person sort of varies. You have the disk, you have another disk where it's a circular shape, but you're approaching it, and parachutes with a low porosity. Streamlined trains, bicycles, and there's been a lot of work looking at bicycles and other things of that nature. If you look at 3D bodies, you have, again, table 7.3, and please take a look at the book 7273 are in the text, and you have a whole bunch of values for those. So B over H for a rectangular plate, ellipsoids, flat-faced cylinders, sharp edges, all of these things all together. Ew. So I have here a square 1.52 meter piling in a 1.52 meter per second water flow that is 6 meters deep. Estimate the maximum bending moment on the bottom of the piling. So I've got seawater, I've got viscosity, I've got a pile width, which is given as 1.152 meters, flow velocity, water depth, okay, all of that stuff. Okay. Reynolds number is going to equal that was wrong on the previous slide. It's new 1.52 times 10 or and that should be oh. So you have a Reynolds number with all the parameters given of 2.26 times 10 to the 5th. C sub d is equal to 2.1. I'm covering that up for some reason. I have the frontal area, which is L times H, which is going to be 6.1 times 0.152, so 0.972 meters squared. Force of drag is then going to be 2.1, 1/2, 1025, 1.52 squared, 0.927, which equals 2,300 newtons. And so that's 2,300 times 6.1 divided by 2, which is 7,015 newtons. You're not doing any calculations here. The previous three lectures, we've been talking about things in terms of the equations of or the various boundary layer equations and how to approach them. Here we're not doing that. We're using tabulated values. Once we have those tabulated values, we're putting it into the equation. So you need to go through those charts, make sure you're familiar with them so that you know what's happening. Airfoils, so a lot of this work, and the whole reason we do this is we want to fly things. Lifting bodies are designed to produce large lift force normal to the free stream with minimal drag. And again, you can see sort of that effect where you have this strong curvature at the front to assist you, and then these very long trailing edges. And again, there's a lot of data out there. NACA from the 1920s and all the way through to today, people have updated these curves. Again, lift is generated by a pressure difference between the upper and lower surfaces. Sharp trailing edge forces the fluid to leave smoothly, inducing circulation and lift. So just regular circulation about the object. As the angle of attack increases, the adverse pressure gradient on the upper surface becomes stronger. At a critical angle, at a certain point, boundary layer separates completely, so around here, and from the upper surface causing stall. So you go from having uniform flow that gently goes over it like this, to one where you see separation, and then ultimately complete separation. And it causes a loss in lift and a sharp increase in drag, because you have nothing to balance anything out. So if you don't have anything to balance it out, then what's going to happen is that you can't use it. So you start to develop various types of C sub L and C sub D curves. C sub L shows a maximum value when you put a flap on there. So a flap is just some sort of airfoil-based shape that you place at the end of the airfoil to allow you a little bit more control. In most cases we look at here, we're not going to put a flap at the end, and instead we're just going to look at some sort of airfoil. I was tempted to say symmetric, but not necessarily. Now in those cases you can see you reach a maximum, and with a flap you have an angle of attack of roughly 2 degrees, but the flap essentially extends it to -12, so you have 14 degrees of operation versus roughly 14 degrees, the same sort of distance in terms of, well, that's 5 to -12, so 17 degrees versus 14 degrees, 13, 14 degrees. Again, can't read the chart that well, but for different Reynolds numbers. And you'll also notice that as you change the Reynolds number, so you go from 3 times 10 to the 6 to 9 times 10 to the 6, you have a larger range that these airfoils can operate because the flow stays attached. Higher Reynolds number associated with higher turbulence is a benefit to you here. You can't do that indefinitely because you pay for that in power, and your component of friction is still pretty important. C sub D with the flap, clearly the flap costs you in terms of fuel. So you try and sort of minimize the blockage effect from that because it's blocking the oncoming flow. You increase your planform area, and as a result of increasing your planform area, you have a greater body force drag, pressure drag. You can also see that in the no flap case, if you fly higher and higher Reynolds number, you have C sub D go down. But remember, C sub D is not a dimensional number. C sub D is associated with velocity. So for a C sub D, can't read that. Okay, I didn't put numbers on there. C sub D associated with that, you have a 9-time increase in the ultimate drag that you're calculating, even though you have a lower C sub D in all of these cases. Lift increases linearly with angle of attack, and it's really kind of neat to look at the NACA 1920 stuff because there's a lot of data out there, and they do show you these sorts of behavior for a whole bunch of different airfoils. Drag remains low at small angles of attack. High lift devices are used to increase CL max during takeoff and landing. So the only time you use them is to essentially have braking or to improve your lift. Nope. With all of this stuff, we've kind of assumed that these are infinite span airfoils. Everything is 3D. So for example, we do a lot of experiments with airfoils in the wind tunnel. We put something called an end plate, which is a very large circular plate on the edge, and that minimizes the 3D effect. But real wings have tips, and that causes the flow to leak from the high pressure bottom into the low pressure top. And it creates wingtip vortices. And so one of the things that if you've taken a plane, gone to Pearson, sort of about to take off, and you've cursed Air Canada, WestJet, or whoever it is that you've had to wait so long, it's because they don't want to flip over by coming in too close behind the person in front of them. And so there's a lot of effort in terms of allowing these things to to bypass the next plane over, but it is exasperating to be sitting in the plane waiting for that to happen. So 3D, so one of the nice things about working in a 2D world, lots of things are easier to define, lots of things are easier to describe. But you have, in 3D, reduced lift, and you have induced drag. And an induced drag is going to go as CL squared over pi aspect ratio, and aspect ratio is going to be B squared over the perimeter of the area. Or the area, the planform area, excuse me. So one of the things, nobody wants to have passenger planes with very large wings, but they're great for gliders. This is not a great figure. I can tell you that that figure was there in 1987 when I took the course. So it's the exact same figure. But what's interesting about it is that the low end minima is not really being achieved yet. We are very close. There's a lot of work that's been done in terms of minimizing C sub D for automotive vehicles. But you can see that it started out with a ridiculously large number of 0.8, and it has since decreased. So most EVs, for example, are in the 0.2 to 0.3 range, which is below where they have that graph. A lot of testing has been done. Now a lot of modeling has been done, particularly with EVs, because they need to extend range and avoid having to pay for drag. A lot of the very interesting tunnels that exist out there have moving tracks so that you can actually test what's happening as the flow goes by, so you can see all of this in action. Small geometric changes significantly alter drag and lift. Okay. And I can, okay, so polymer additive, okay, yeah, all right. Research has covered many advanced methods to reduce drag, polymer additives. So for a while there, they were looking at ways of improving things like, for example, fire response. So they wanted to add within various types of fire hydrants or the water system supporting them. They wanted to use polymer addition, and it results in a significant drop in drag within the piping system and better flow out, which improves the amount of water that you can have. That hasn't done very much. It's used in the Trans-Alaska pipeline because there's not going to be any cross-contamination with drinking water, but okay, it's limited. Surface riblets were really, really exciting in the late 80s and late 90s because they work. So essentially this was using the idea of shark skins. Shark skins have this weird roughness to them that are very small roughness elements. And you know that roughness elements, if you put them below the viscous sublayer, can do some interesting things in terms of adjusting things. They have been used on racing yachts, not so much on aircraft, because the biggest problems with riblets is that I fly an aircraft and I get the drag reduction, but then if I want to turn it around, I've got to clean it. And the cleaning costs far outweigh any benefit that I get from it. Microbubble injection has not been that great. All right, so there we go. You can inject small bubbles. You essentially sort of create a cushion between the wall and the flow, and that does reduce air, but it costs a lot of money to do it correctly, especially if you have a large amount, large volume of water that you want to move. It's nice because it doesn't cause problems. Active flow control, so I do a lot of research in that area. Tangential blowing, synthetic jets, lots of different approaches to it. Again, very interesting. is the maintenance cost, and we've looked at ways of dealing with it. Questions? Just want to get to where I am. There we go. I'm going to do a couple more examples, and again, my plan right now is that on Tuesday, I will present this course summary, and I will start on one of the final exams. I don't know which one. For section 2, I will do the same thing, do a different final exam, and then for the last lecture for section 2, another final exam, and then everything is sort of released. Okay, same sort of thing. This is from White. Smooth ball versus rough ball. Again, not a great graph. Okay, I mean, I was looking for the one that I found that I gave you earlier in the lecture, but estimate the drag force for a normal rough baseball. So if you've played baseball, you know that you have a lot of threads on the surface, and those threads are really important in order to give you that roughness, and that's what gives you the transition. You could always, and there's lots of ways to manufacture them, make a perfectly smooth one. So rough transition is about 100 miles an hour. So roughly around there. Smooth remains laminar. So tunk, 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 over there. So same sort of thing. You've got air. You've got the slots per cubic foot there. Area. That's the circular cross-sectional area, the planform area as it approaches. And so say 108.1 or 157.5 feet per second. Ooh. So if you calculate the drag force for the two cases, it's the same thing as what we saw with the golf ball. In one case, you have a very low coefficient of drag, 0.25. You pay for it with increased friction, but that's not a significant part of the actual drag that you're dealing with. You have the same velocity, fluid, and everything else, but C sub D has gone up by a factor of 2, so from 0.25 to 0.5. And all I have to do is take my value from the previous case, which is not 0.34, it's 0.34 something, something, something. And I end up with an F of D, which is equal to 0.69 pounds force. Questions? I have an iceberg. It drifts with the wind. It's exposed, so this is sort of, it's not a great model because it's sort of a cube, but there you go. Flat cylinder, so drifts with the wind. Air drag equals water drag, and so you say C sub D for the air versus C sub D for the water, and the big difference is going to be the difference in the relative velocity on the top, and on the bottom it's just velocity of the water. Okay. Rho C sub D, area sub. Ugh. Rho of air, CD of air, area of the top. So if you combine all the terms together, you'll get a ratio between density of water, C sub D for water, and the two areas with respect to air for the same quantities. And if I okay. If I let u minus v be some sort of function of alpha, I can sort of do the ratio between the two, and the velocity of the berg is equal to velocity of the wind divided by 1 plus square root of alpha, and v is typically 2 to 3% of the wind speed. So it's not a surprise. It's not a surprise. You don't expect to have an iceberg traveling at the same velocity as the wind. Otherwise, we would be in a lot of trouble on shipping routes. Go ahead.
No, I just wanted to ask what that says. The velocity of the iceberg.
I'm sorry?
That says V sub berg, right?
V sub berg, yes. My handwriting is never going to get better. Okay. I'm going to try and do this really quickly, and we'll stop after this one. Sand. So you love sand because you've seen sand roughness is really important to your chapter 6 work. So C sub D E 1/2 rho of the wind. So you have sand in an upward water flow. Find the minimum velocity to carry all the particles up. Must lift largest particle, which is 250 microns. So drag equals weight, W minus FB. V squared, pi over 4, D squared, rho sand minus rho weight or water, G pi over 6, D cubed. So all I'm doing is creating a ratio between drag force, which I know is going to be related to C sub D, and I want it, and this is going to be more confusing than it's worth. This is diameter. If you normalize it, you'll end up with 0.0555. If you then look at the chart, low Reynolds number of 10 is probably reasonable. You can calculate this on your own. You end up with a Vmin of 0.04 meters per second, which is why that when you walk into the water, say in a lake or on the beach, you will still kick up water despite the fact that you haven't, or kick up sand, even though you haven't walked very quickly. Any questions on this really quickly? Go ahead.
What is the projected area we're looking at for the iceberg?
For the
Is that